Astronomers have once again turned their gaze beyond the boundaries of our solar system into the vast interstellar void, scattered with icy fragments and rocky drifters that have wandered among the stars for billions of years. Recently, they announced the discovery of a mysterious new object, potentially only the third interstellar visitor ever detected. Temporarily designated A11PL3Z, this celestial traveler is now moving along a vast, elongated path, steadily approaching the Sun. In just 4 months, it will reach its closest point to our star, before likely vanishing into the depths of space once more. It's merely passing through. But what do we actually know about it? In all of astronomical history, such visitors from beyond have been spotted only twice before. The first and most famous was Oumuamua, a name meaning messenger from afar arriving first in Hawaiian. It stunned scientists with its bizarre shape somewhere between a cosmic cigar and a flattened disk, and with its unexplained acceleration, which defied all known models. Then, in 2019, came Comet Borisov, the second confirmed traveler from another star system. Its passage through the inner solar system proved that interstellar objects do occasionally cross Earth's orbital path. Now, A11PL3Z joins this exclusive group, already sparking intense curiosity among astronomers. According to orbital calculations, it's hurtling through space at an incredible 245,000 kilometers per hour. To put that in perspective, at such speed, it could cover the distance from the Moon to Earth in under 2 hours. The orbit itself is just as remarkable. Its eccentricity, a measure of how stretched an orbit is roughly 6 times greater than that of objects bound by the Sun's gravity. Anything with an eccentricity greater than 1 follows a hyperbolic trajectory, meaning it's not gravitationally captured, but simply passing through. In short, this new visitor truly appears to come from the depths of interstellar space, crossing our solar system on its long journey between the stars. Observatories around the world have already launched a large-scale campaign to study the object. It is currently within the orbit of Jupiter and is steadily moving toward Mars. By October, it had approached a region of space close enough for ground-based telescopes to obtain detailed data on its composition and surface. Preliminary estimates suggest the object could be approximately 20 kilometers in diameter, roughly the same size as the largest comets ever observed, and even larger than some asteroids believed to have caused mass extinctions in Earth's distant past. Fortunately, there is no cause for concern. This visitor poses no threat to our planet, so don't spend your savings just yet. Its trajectory will not intersect Earth's orbit. In fact, it will pass on the other side of the Sun, eliminating any possibility of a collision. However, for astronomers, this alignment is a real coup. It allows them to safely monitor whether a fragment of the hypothetical coma or tail could be cutting through nearby space like a knife through butter. Since this is only the third known interstellar object, researchers remain cautious in their conclusions. At first glance, such cosmic travelers seem extremely rare, but there is growing evidence to suggest they may be much more common than previously thought. In the early stages of planet formation, young systems are extremely unstable. As massive planets form and begin to gravitationally interact, they can eject vast amounts of material into the void. Current models suggest that each planetary system could eject billions of icy or rocky fragments into interstellar space, countless silent wanderers drifting between the stars. In essence, our galaxy is teeming with wanderers, countless fragments of rock and ice drifting between the stars, like travelers passing through a busy metro station. Most remain invisible, hidden by their faint glow and dark surfaces. The rule is simple. The smaller and darker an object, the harder it is to detect. Interstellar bodies also move far faster than ordinary asteroids or comets, racing through the solar system in a matter of weeks or months. That's why astronomers were exceptionally lucky. This time, the new object was detected well before its perihelion, its closest approach to the Sun. By contrast, Oumuamua was only discovered after it had already passed that point and was on its way out. This early detection gives scientists a rare chance to gather an enormous amount of data, including high-resolution images, months before the object disappears back into the void. But what makes these interstellar visitors so important? Above all, they offer a direct glimpse into the material of another solar system. Through spectroscopy, researchers can analyze the light reflected from the object's surface and determine which compounds it's made of. In the case of Comet Borisov, for instance, spectral analysis revealed traces of cyanide gas and other volatile substances astonishingly similar to those found in comets from our own Oort cloud. This discovery led scientists to suspect that the chemical makeup of young planetary systems might be strikingly consistent no matter which star they form around. The case of A11PL3Z is even more intriguing. So far, there's no evidence that it emits gas. If that remains true, it would make this only the second known rocky interstellar object. But another possibility is still on the table. As it draws closer to the sun, its surface will heat up, and beneath its dusty crust, ice could be hiding. If that ice begins to sublimate, a coma and tail will form, officially classifying it as a comet. Some might be disappointed if it turns out to be just a comet. But trust me, it would be a spectacular one. A wide range of instruments are already being prepared for observation. Optical telescopes will measure its brightness and shape, while radio telescopes can detect molecules evaporating from its surface. Infrared observatories will estimate its thermal radiation, allowing scientists to refine its size and thermal properties. And, of course, ufologists will eagerly begin writing the next chapter of their research. In any case, the more data we gather, the more accurately we can trace its true origin, and that's what makes it fascinating. Precise trajectory tracking is especially valuable. Even the slightest deviation from a predicted path can reveal uneven outgassing or unusual physical properties. That's exactly what happened with Oumuamua. Its motion deviated slightly from what gravity alone could explain, sparking years of intense debate. One theory attributed the anomaly to reactive outgassing material evaporating from one side, gently pushing it forward. Another suggested the cause was radiation pressure from sunlight acting on an extremely thin, lightweight object. That latter idea led to one of the boldest hypotheses yet, that Oumuamua might have been an artificial solar sail built by an advanced civilization. While most experts consider such theories unlikely, the very fact that they're being discussed reveals just how little we truly understand about objects arriving from the interstellar abyss. There's another remarkable aspect to this story. The discovery of this new object has united an extraordinary global effort. Hundreds of astronomers from dozens of countries are now collaborating through an international data-sharing network, and every single measurement adds a piece to the puzzle. Even amateur astronomers have joined the search. With telescopes as small as 30 to 40 centimeters in diameter, they can record the object's motion and refine its orbital path, providing valuable data for professionals. In recent years, astronomy has undergone a quiet revolution thanks to automated sky surveys. Networks such as Pan-STARRS and the Catalina Sky Survey sweep across enormous portions of the heavens, photographing them in high resolution. Sophisticated algorithms then track the motion of faint points of light, the very process that led to the discoveries of both Oumuamua and comet Borisov. The next generation of observatories, like the Vera Rubin Observatory now nearing completion, will be even more powerful. In the coming decade, the discovery of interstellar visitors may become almost routine. And yet, even if one day we find dozens of them each encounter, like A11PL3Z, will still feel special. It's like meeting a time machine at a cosmic crossroads built by Dr. Emmett Brown, pausing for just a moment before continuing on its endless journey. Each carries the secrets of other stars and other eras. From its surface, we can extract clues unreachable, even by our most distant spacecraft. After all, no human probe has yet ventured far enough to witness the birth of other planetary systems. Objects like this remind us that the cosmos is not empty, far from it. It's alive with wandering worlds, forgotten stories, and fragments of matter that once belonged to other suns. In just a few months, A11PL3Z will vanish back into the darkness. But the knowledge it leaves behind will continue to ignite our imagination for years to come. Every new observation brings us one step closer to understanding just how rich and intricate our cosmic neighborhood truly is. Such exciting times, star comrades. If you'd like to support the channel, please consider leaving a like, subscribing, or sharing your thoughts in the comments below. And now, let's turn to remarkable discovery of this year, a strange new traveler from the depths of space, 3I Atlas. It's the third confirmed interstellar visitor in recorded history, and it's already making waves across the astronomical community. In recent weeks, scientists have confirmed the presence of water in its coma, even at a great distance from the sun. They've also managed to estimate the size of its active zone and observe its cometary physics in real time, a rare and thrilling opportunity. But before we let our imaginations run wild with visions of alien spacecraft, let's look at what our telescopes from Hubble to Swift have actually seen and what conclusions we can draw. It all began quietly on July 1st of this year. The Atlas automated survey in Chile detected a faint but distinct object following an extremely elongated, almost linear, hyperbolic trajectory, the key signature of an interstellar origin. Its orbit is not closed, and its speed is so great that not even the sun's gravity can hold it. It will simply pass through and vanish back into interstellar space. Even at this early stage, it was clear this wasn't just another comet. It was something truly alien, a visitor from beyond. And time was short. The race to study it had begun. Among the first to capture it was the Hubble Space Telescope, which produced crisp images revealing a teardrop-shaped coma, a short tail, and fine dust, everything characteristic of a comet. Except this one came not from our Oort cloud, but from the void between the stars. From these observations, astronomers could only place an upper estimate on the nucleus's size on the order of a few kilometers, since its light is blended with the surrounding dust. But one thing was certain. This was no barren rock. It was alive with activity. These July Hubble data, published by NASA on July 21, became the foundation for the first morphological models and hypotheses about the comet's dust composition. Then, in a stunning development just days later, the Swift telescope detected ultraviolet emissions from a distance of 3.5 astronomical units, unmistakable evidence of water decomposition. Water appearing far beyond the distance where ice normally awakens under solar heating. Its activity level, estimated at about 20% of the surface, is unusually high for a comet at such a distance. The explanation seems clear. Much of that water doesn't come directly from the nucleus, but from large ice grains ejected into the coma, slowly vaporizing there. This behavior has been seen before in a few distant solar comets, but never before in an interstellar one. But the most fascinating thing about 3I Atlas is its changing velocity. Strange, isn't it? Almost as if something or someone were controlling it. Creepy? Maybe a little, but it's too early to be afraid. Yes, the velocity of 3I Atlas does change, but exactly as celestial mechanics predicts. At the time of its discovery, the object was moving at about 60 kilometers per second. As it swings around the sun, at its perihelion, the closest point in its orbit, that speed increases to nearly 68 kilometers per second. However, the real intrigue lies elsewhere. Besides the sun's gravitational pull, could the comet be slightly accelerating due to jets of gas and dust erupting from its surface? That's common for active comets. Their outgassing jets act like tiny engines, providing subtle thrusts. By studying these effects, astronomers can learn what the comet is made of, where its active regions are located, and how it rotates. For now, the orbital data for 3I Atlas appear perfectly normal. A clean, straight hyperbolic trajectory with no unexplained deviations. Observations continue as teams around the world check whether these small interstellar nudges could be responsible for any anomalies. What's certain is that the comet is highly active, as clearly shown by both photographs and spectroscopic data. Now, let's move to the next breakthrough, the discovery made by the James Webb Space Telescope. James Webb has one of the most critical roles in this mission: to break down the faint light of the coma into its chemical components: ice, water, carbon monoxide, carbon dioxide, CO2, and organic compounds, and to compare their abundance to those found in comets within our own solar system. The plan is to observe 3I Atlas both before and after its closest approach to the Sun. At its minimum distance, about 1.8 astronomical units from Earth, the telescope will measure how the composition and size of its particles evolve over time. James Webb may also be the only instrument capable of detecting the faint spectral lines of CO and CO2, if they exist at all. These measurements could finally solve the biggest mystery: why, despite clear signs of water, are classic cometary gases not appearing as strongly as expected when the object nears the Sun? Or perhaps it isn't really a comet. According to official NASA data, the James Webb Telescope is central to the investigation in the months ahead. Meanwhile, ground-based observatories, including the Very Large Telescope, VLT, Gemini, IRTF, and several sky survey projects, have already built up a rich archive of images and spectra. Early analysis shows a distinct spectral bias in the visible range, typical of organic-rich dust, similar to that seen in D-type comets and in 2I Borisov. This suggests that the surface of 3I Atlas has been exposed to cosmic rays for a long time, forming a tough organic crust. Such a layer could theoretically seal off the volatile materials beneath, preventing gas release while allowing large water ice grains in the coma to appear earlier than lighter gas species, such as CN or C2. In other words, what we're seeing might be a frozen messenger, cloaked in an ancient carbon shell, whispering the chemistry of another star system. We now face another profound question. Where did Comet 3I Atlas come from? Current kinematic analysis suggests its path is linked to the thick disk of our galaxy, a region populated by ancient, metal-poor stars. Yes, the universe has its own form of poverty. This clue carries deep cosmochemical significance. If the parent system was poor in heavy elements, then water ice would have been abundant, while carbon monoxide and carbon dioxide was scarce. Research indicates that stars in this region are at least 8 billion years old, predating our own solar system, perhaps by billions of years. That makes 3I Atlas a strong candidate for the oldest comet ever observed, even if only by indirect evidence. And, of course, its mystery and spectacular appearance have inspired wilder ideas. Some people believe they're witnessing not a comet, but a spaceship. In recent weeks, countless articles, some scientific, others decidedly less so, have speculated about its technological nature, urging astronomers to search for non-gravitational anomalies that might hint at artificial control. From a scientific standpoint, the test is simple. If the comet accelerates beyond what gravity predicts, that acceleration must correspond to a measurable mass flow of gas and dust, which we can detect through spectral emissions and coma photometry. And we already see water and dust. That means the natural propulsion mechanism is fully active. So it doesn't matter who's at the helm. Even if it were a spaceship disguised as an ice-spraying comet, the same physics would still apply. 3I Atlas will remain visible from Earth until the end of September. Then it will vanish into the sun's glare, reappearing again in December. That will mark our second chance for spectroscopy and high-sensitivity imaging when the inner solar system grows warmer and the comet's activity or even fragmentation may intensify, just as it did with 2I Borisov. Ideally, we'll witness the evolution of its coma shifts in particle size, the emergence of new volatiles, changes in tail structure. These data will let us constrain the comet's porosity, thermal conductivity, and rotation, revealing the geography of its active regions. There's an important detail here. Changes in a comet's velocity can reveal its inner physics. For a visitor moving tens of kilometers per second, even small non-gravitational accelerations are difficult to measure. That's why long-term, high-precision observations are critical. The Swift telescope's water detector plays a key role linking the observed luminosity to the momentum transferred as water vapor escapes. If we detect a rise in outgassing this autumn, followed by a predictable, small orbital shift, it would directly confirm the natural explanation. But if activity increases and the orbit remains almost unchanged, that would be intriguing too. It would suggest that reactive forces are minimal, pushing us to explore deeper layers of cometary physics, jet directions, ejection anisotropy, and particle mass distribution, the subtle inner workings of natural engines, not alien propulsion. And that brings us to an even grander perspective, the galactic story. The age and kinematics of 3I Atlas suggest that icy bodies like it were forming and being ejected into interstellar space very early in our galaxy's history, in environments poor in heavy elements. This means the raw ingredients of comets, water ice, and simple volatiles existed even when metals were scarce, and that planetary migration, tidal disruption, and ejection mechanisms were already shaping young worlds. For the first time, we have a sample, however, distant from that ancient epoch. Its dust and ice are a time capsule, sculpted by cosmic rays over billions of years. By comparing its spectra with those of Borisov and solar system comets, we can finally test how universal the chemistry of ice and rock truly is. And since we've now reviewed all that is currently known, we can say this much. 3I Atlas is not an alien craft, flashing its navigation lights, at us at least, not yet. But it is a kind of spacecraft, a vessel from another era, launched not by civilization, but by the dynamics of a young galaxy. We watch as it sails past, analyzing its spectra, deciphering the composition of its water and dust, as if reading ancient seals from the dawn of time, and then releasing it back into the dark. We do not part empty-handed, but with a realization. Comets are not unique to our solar system. They are the universal language of planets, spoken throughout the Milky Way. If all the data align, for the first time, we will draw a chemical portrait of an ancient interstellar comet, tracing its transformation from frozen dust in the distant cold to a fiery traveler near the sun. Or perhaps we are witnessing the ancient technology of long-vanished civilizations. What do you think, star comrades? New images from Mars 3I Atlas has been spotted again, and this time it doesn't look like a comet. A perfect glowing cylinder drifting across the Martian sky has been captured by the rover. No visible tail, no fragmentation, just structure. It makes you want to shout, do you realize what's happening right now? It sounds unbelievable, but what exactly are we seeing here? Let's get to the bottom of it. Recent photographs of the interstellar comet 3I Atlas, taken during its closest approach to Mars, have understandably ignited a storm of debate online. Social media users are buzzing with speculation about the object's nature and origin, drawing attention to its unusual shape. And yes, it's true. NASA's Perseverance rover captured the object streaking across the Martian night sky. The event was recorded by the rover's right-hand navigation camera located in Jezero crater. NASA later released the images in raw format, and soon after, the internet exploded with amateur renderings and interpretations. It's the peculiar, elongated appearance of 3I Atlas in some of these images that sparked new theories, suggesting it might be more than a comet. Some users even compared its shape to ancient petroglyphs depicting elongated, elliptical figures. But as is often the case, the truth turned out to be far more ordinary. The elongated form seen in the images doesn't represent the comet's real shape. It's an artifact of motion caused by the long exposure time. Here's the technical side. Perseverance's navigation camera has an angular resolution of about 12,500 kilometers per pixel, given the comet's distance from Mars, roughly 38 million kilometers. The streak that appears in the photo spans about 50,000 kilometers in apparent length, vastly exceeding the comet's true diameter. Similar optical illusions have fooled us before. For instance, in March of last year, images from a lunar orbiter appeared to show an elongated craft flying above the moon, which later turned out to be the Korean lunar probe Danuri, misinterpreted because of relative motion and camera exposure settings. Even so, it's hard to ignore the sense of wonder. An incredibly rare visitor is once again hurtling through the solar system, the interstellar comet 3I Atlas. Astronomers have been astonished not only by its carbon dioxide-rich composition and unexpected color shifts, but also by its potentially colossal size. And that's not all. The oddities are only beginning. So sit back, you're going to enjoy this one. But as always, let's start from the beginning. So, Comet 3I Atlas is blooming before our very eyes. Let's call it that for now, at least. It has suddenly begun to glow a brilliant green, drawing the attention of astronomers all over the world. Normally, this emerald hue in comets is caused by dicarbon molecules C2 fluorescing in their gaseous envelope. But in this case, those molecules are almost absent. Scientists suspect the strange glow might arise from rare chemical reactions or even internal processes within the comet's nucleus mechanisms that activate at specific temperatures, like switches flipping on as it nears the sun, transforming its appearance in an instant. But this mysterious green glow is only one of 3I Atlas's many peculiarities. Current models suggest that the diameter of its nucleus could reach 5 kilometers, roughly the size of a small city. That's about a 10-15 minute bus ride, or an hour's walk, or 6 hours of crawling if you're a spy. In other words, this object is 1,000,000 times more massive than the first interstellar visitor, Oumuamua, which measured only about 110 meters across. Preparations are now underway to use NASA's HiRISE camera aboard the Mars Reconnaissance Orbiter to observe the comet in unprecedented detail. These high-resolution images will allow scientists to estimate the nucleus's size directly from its reflected light, confirming or refuting the current mass calculations. If 3I Atlas truly exceeds 5 kilometers in diameter, it would make it exceptionally large for an interstellar object. And such rarity raises inevitable questions. How could something this massive have formed, and could it even be artificial? The next few weeks and months of observation may hold the answer. As for its acceleration, it's about 4.6 meters per day, caused by the comet losing material gas and dust as sunlight heats its surface, producing a faint but measurable thrust. Using data on this outflow velocity, astronomers estimate the nucleus's mass at more than 33 billion tons. This aligns with upper limits derived from Hubble Space Telescope observations, confirming 3I Atlas as a truly colossal interstellar traveler. But perhaps the most hotly debated feature in recent days is the appearance of a solar tail, a bright, extended structure that seems to point toward the sun rather than away from it. How can that be? After all, ordinary comets form tails as solar wind and radiation pressure push dust and gas outward, always in the opposite direction of the sun. In the case of 3I Atlas, the situation appears to be the exact opposite. Several hypotheses have been proposed to explain this effect. The most conservative one involves the scattering of light on dust particles. If the comet's coma is dominated by nanoparticles or has an unusual internal structure, light may refract and diffract, a process in which waves of light, sound, or even electrons bend around obstacles or pass through openings, deviating from a straight path and spilling into the shadowed regions. The result can be an optical illusion. The glow seems to point toward the sun, when in fact it does not. Another hypothesis points to the interaction between charged particles and the interplanetary magnetic field. In this case, the trajectories of ejected gas and dust are shaped not only by the solar wind, but also by electromagnetic forces, which can redirect the tail and produce this peculiar geometry. And of course, we can't overlook the unofficial explanation that always resurfaces in such debates. What if this isn't a comet at all, but a cloaked alien ship using its tail like a solar sail to maneuver? From a scientific standpoint, that's extremely unlikely, but it remains a popular topic among amateur astronomers. The comet's chemical composition also plays a major role. Observations show a record-breaking carbon dioxide to water ratio, the highest ever seen in any known comet. This suggests unusual formation conditions, perhaps in a cold, metal-poor region of space. Such a ratio can make gas emissions behave differently from those of typical water-dominated comets, creating localized luminous structures that resemble a reverse tail. Some researchers argue this is due to a complex interplay of gas dynamics, electromagnetic fields, and radiation effects. Others, the champions of alternative hypotheses, see in it a deeper anomaly, signs of materials or structures never before observed. Exciting? Absolutely. But the scientific community remains cautious. If humanity ever does receive a message from another civilization, it probably won't come in the form we imagine, not a shining beacon pulsing through the void saying, "You are not alone." Reality, as always, has a way of defying expectations. So, let's draw a parallel. Do you remember that supposed first contact, the one simply called the wow signal? If it really was contact, it almost slipped through history unnoticed, just a line of numbers on a yellowing printout from an old radio telescope, buried for decades in a dusty archive box. It all began, quite unremarkably, on the 15th of August, 1977, at Ohio State University. Radio operator Jerry Eman was reviewing data from the Big Ear telescope, the same routine he'd done 1,000 times before. Nothing unusual. Columns of numbers indicating radio noise at different frequencies, with the occasional spike that usually turned out to be terrestrial interference or random static. But that day, something caught his eye, a series of numbers and letters lining up in a single, narrow, yet incredibly strong band. The signal was so intense, it leapt off the page, shining from the noise like a flashlight in the dark. Startled, Eamon circled the sequence in red ink and scribbled one word in the margin: "Wow." His reaction was understandable. At first glance, this might have been dismissed as a historical curiosity, except for a few remarkable details. The signal lasted 72 seconds, the maximum possible time a source could remain in the Big Ear's narrow beam as the Earth rotated. It appeared exactly at 1,420 megahertz, the hydrogen line, a frequency protected from terrestrial broadcasts and long considered by astronomers the ideal band for interstellar communication. It was 30 times louder than background noise and had the precise intensity curve expected from a natural sky tracking signal. And then it never appeared again. After dozens of follow-up scans, the source was gone. No repetition, no pattern, no trace. Almost immediately, the world of science split into two camps: those who saw it as a possible whisper from intelligence beyond Earth, and those determined to find a mundane explanation: satellites, reflections, instrumentation errors, even microwave ovens. Officially, the consensus remains cautious. A single detection, after all, proves nothing. But the wow signal refuses to die. It lingers mysterious, resilient, unaccounted for. Every explanation proposed over the decades has stumbled against the data. The more it was studied, the stranger it became. By the early 2000s, a new idea gained traction: comets. Comets, surrounded by vast clouds of hydrogen gas, can interact with solar radiation and emit faint radio signals in the same frequency range. Then, in 2016, astronomer Antonio Paris proposed a specific theory. He pointed to comets 266P Christensen and 335P Gibbs, which were located in roughly the same region of the sky as the WOW signal. Their hydrogen envelopes, he suggested, might have produced a short, powerful burst of radiation, mimicking an extraterrestrial transmission. It was a tidy solution. Everything natural, everything explainable. But almost immediately, new questions arose. The signal profile was too clean. Cometary radiation is typically diffuse, stretched out across time and space, not a sharp, solitary spike. And when astronomers rechecked the comet's trajectories, the data didn't quite match. The orbits were uncertain. It wasn't clear whether they were even in the right patch of sky in 1977. In the end, the comet hypothesis remained just that: a possibility, not a resolution. Plausible, yes, but fragile. Too many ifs. And now, almost half a century later, that same mystery seems to echo again in the appearance of 3I Atlas. What if the source of that 1977 signal wasn't a comet at all, nor background noise, nor radio interference, but an interstellar wanderer, a visitor silently passing through the solar system? What if it wasn't just a chunk of ice and rock? If so, the WOW signal might have been our first encounter with an interstellar object, one we detected not through the eyes of telescopes, but through the ears of a radio dish. Of course, this hypothesis is provocative. It raises far more questions than it answers. Could an interstellar object truly emit radiation at the hydrogen line frequency? Naturally, that seems unlikely. And yet that ever-present hint of artificial origin reappears. So whose signal could it have been? A random transmission from a distant starship? A deliberate beacon? Or simply the projection of our own minds, our habit of putting a little green mask on every strange rock that drifts our way? This is precisely where science and imagination meet. Without a repeated observation, we remain prisoners of conjecture. A single signal proves nothing. And yet, those who believe in extraterrestrial intelligence argue that rare anomalies like these may be the keys, the fleeting moments when the universe whispers something it doesn't repeat. After all, interstellar travelers like Oumuamua and 3I Atlas have already proven that space is full of strangers, visitors, crossing our cosmic neighborhood without notice, without permission, and without announcement. Who's to say one of them hasn't already sent a message? Or that we haven't already heard it and simply didn't recognize it for what it was? The mystery of the WOW signal sits perfectly at the crossroads of two great traditions. One, the rigorous, skeptical discipline of science, demanding data, repetition, and proof. The other, the boundless human yearning to find meaning, to glimpse a sign where chance may hide. Whether something similar will unfold with 3I Atlas, only time will tell. But perhaps, as always, the truth lies somewhere in between. So what do you think? On the 19th of October 2017, astronomers working with the Pan-STARRS 1 telescope in Hawaii noticed something unusual: a faint, fast-moving speck of light drifting across the sky. At first glance, it seemed unremarkable, just another dim object among the thousands of asteroids and comets discovered every year. At the time of detection, it was about 30 million kilometers from Earth. Small celestial bodies like this are common throughout our solar system. Most inhabit the regions between Mars and Jupiter, or lurk far beyond Neptune and Pluto in the Kuiper Belt, and even farther still in the vast Oort cloud, but Auro Espoaces, a spherical halo believed to be the source of long-period comets. But this new cosmic wanderer turned out to be anything but ordinary. When astronomers traced its trajectory, they discovered something astonishing. This object did not originate within our solar system. It had come from the distant stars, becoming the first interstellar object ever observed by humanity. It entered our system at a blistering 30 kilometers per second, following an extremely elongated hyperbolic orbit, slicing through the plane of the ecliptic almost at a right angle, and passing within the orbit of Mercury. By the time of its discovery, 40 days had already passed since its closest approach to the Sun. At first, scientists classified it as a comet, designating it C2017U1. Its peculiar orbit was already noted, And to confirm any cometary activity, the Very Large Telescope in Chile launched emergency observations under a special program titled Urgent, First Interstellar Object in the Solar System. But when the composite images arrived, they revealed no coma, no gaseous halo, no visible tail, only a bare, solid nucleus. As a result, C-2017 was reclassified as an asteroid and renamed a 2017 U1. Soon after, the Discovery team proposed a more poetic name, Oumuamua, a Hawaiian word meaning scout or messenger from afar, arriving first. It's worth noting that another name had also been considered Rama after the alien spacecraft discovered under eerily similar circumstances in Arthur C. Clarke's science fiction novel Rendezvous with Rama. Oumuamua, as the first interstellar object ever discovered, forced astronomers to rethink their classification system entirely. To accommodate it, the International Astronomical Union created a new designation, the capital letter I for interstellar. Thus, the visitor officially became 1I, 2017 U1, Oumuamua, the first of its kind. At first, scientists believed that this interstellar traveler was a rocky body, shaped like a long, slender cigar, roughly 300 meters in length and 30 to 40 meters wide. But later, analyses painted a different picture. Another group of astrophysicists proposed that Oumuamua was actually much flatter, not a cigar, but a pancake-like disk, thin and broad, unlike anything seen before. Even more intriguingly, the object appeared to be gradually thinning as it moved through space. The surprises didn't stop there. Using the William Herschel telescope, astronomers obtained its spectral profile and discovered a uniform red hue across its surface, similar to that of many objects in the Kuiper belt. This reddish coloration is typically the result of cosmic ray bombardment high-energy particles, primarily protons, striking an object's surface over millions of years. It suggests that Oumuamua's outer layer has been heavily weathered by deep space radiation. Yet despite its unusual appearance, researchers are confident that Oumuamua is primarily composed of ice, not rock. They modeled how various types of ice would sublimate, that is, transition from solid to gas as the object passed near the sun. They calculated its mass, albedo, reflectivity, and the recoil forces created by outgassing, comparing these parameters to the properties of known ices. Only one material matched the data closely: solid nitrogen. This substance is already familiar to scientists. It covers much of the surface of Pluto and other icy bodies in the outer solar system. From these findings, the researchers proposed that Oumuamua might be a fragment of a Pluto-like exoplanet, one that once orbited another star before being ejected into interstellar space. However, not long after, on the 27th of June 2018, astronomers made a surprising announcement. Oumuamua was not an asteroid after all, but a moderately active comet. This conclusion came from precise measurements of its non-gravitational acceleration, a subtle, continuous push consistent with the outgassing seen in comets. As the object neared the sun, its speed increased as though it were being repelled by solar radiation itself. But there was a problem. The acceleration was too strong to be fully explained by known mechanisms, and strangely, Oumuamua showed no visible tail, the classic signature of a comet. So what was it, really? To investigate further, astronomers studied its motion and rotation. The object appeared to tumble chaotically through space, rotating around 3 axes with a period of 7 to 8 hours and a brightness amplitude of about 1.8 magnitudes, meaning it reflected sunlight very unevenly as it spun. Its dry surface, peculiar shape, and enigmatic path soon led some researchers to propose a provocative idea. Could Oumuamua be an artificial probe, a fragment of alien technology drifting through our solar system? It's an exciting thought, but the evidence points elsewhere. No radio signals were detected, and the object's color and reflectivity suggest a natural composition. Later, computer simulations offered a compelling natural explanation for its bizarre properties. In this model, Oumuamua is a fragment of a planetary body that once passed dangerously close to its parent star, close enough to be torn apart by tidal forces. The resulting debris was flung outward by gravitational turbulence, hurled into the void between stars. We've seen this kind of cosmic violence before. In 1994, comet Shoemaker, Levy 9, passed too near Jupiter, where tidal forces ripped it into 21 separate fragments, all of which later plunged into the gas giant's atmosphere. In the same way, the model showed that when a rocky or icy world grazes its star, tidal forces can deform, flatten, and even fuse pieces together into long, thin shapes exactly like Oumuamua. Such fragments can be heated, compressed, and then ejected at incredible speeds, fast enough to escape their home system entirely. Oumuamua entered interstellar space, traveling about 30 kilometers per second, but as it neared our sun, gravity accelerated it to a perihelion velocity of roughly 88 kilometers per second. After swinging past its closest point to the sun, it changed course slightly, passing beneath the orbits of Mercury and Earth, and then crossing the ecliptic plane once more, this time in the opposite direction, through the region between Earth and Mars. Now, the object is on its way out, departing the solar system toward the constellation Pegasus. Over the coming decades, its speed will gradually slow back to what it was upon arrival as it drifts ever farther into the interstellar dark. In about 20 years, Oumuamua will finally leave the solar system forever, a silent messenger from another star, vanishing into the endless night. It remains unknown how long Oumuamua has been traveling through the galaxy. It could be hundreds of millions or even billions of years. By tracing its trajectory backward, astronomers found that it appeared to have come from the direction of the constellation Lyra. If it had originated near Vega, its journey would have taken about 600,000 years. But there's a catch. 600,000 years ago, Vega and its neighboring stars were in completely different positions. Oumuamua could not have come from there. Current models suggest a more distant birthplace, a star system in the constellation Carina, from which it may have been ejected around 45 million years ago. Since then, that region has drifted slowly southward in our sky, imperceptible to the naked eye but measurable to astronomers. Given such extraordinary properties, one question seemed inevitable. Why not send a probe to Oumuamua? Why not see, once and for all, whether it's a comet, an asteroid, or something far stranger? And indeed, on the 30th of October 2017, the Lyra project was proposed a bold plan to design and launch a spacecraft capable of catching up with the fleeing interstellar visitor. But there was one major problem. By the time of its discovery, Oumuamua was already on its way out of the solar system, traveling at nearly 88 kilometers per second. For comparison, the Parker Solar Probe, the fastest human-made object in history, reaches about 95 kilometers per second, but only when diving toward the sun. Planning, building, and launching a deep space mission typically takes years, even in the best circumstances. By the most optimistic estimate, preparing a pursuit mission to Oumuamua would have required at least 5 years. And that's before addressing the cost, hundreds of millions, if not billions of dollars. Even if engineers managed to design a spacecraft traveling twice as fast as Parker, it would still need a decade to catch up. By then, Oumuamua would be so far from the sun that solar power would be useless. Such a mission would require radioisotope thermoelectric generators, nuclear batteries capable of producing electricity for decades, but their output declines steadily over time. And in the end, the scientific payoff seemed too uncertain. The odds that Oumuamua was actually connected to an extraterrestrial civilization were vanishingly small, not enough to justify such an enormous investment. Had it been discovered earlier, as it approached the solar system, even a few years before its closest pass, things might have been different. A mission might have been launched, not to chase alien life, but to study the first interstellar object up close, something of immense scientific value in itself. But after weighing all the risks, timelines, and costs, the Lyra project was ultimately cancelled. And so, today, the lonely wanderer Oumuamua continues its journey outward, forever leaving our solar system behind. Yet, its brief visit changed everything. It gave astronomers around the world a treasure trove of data and a profound reminder that the void around us is far from empty. Just 2 years later, in 2019, another traveler arrived, the interstellar comet 2I Borisov. Its discovery confirmed what many had begun to suspect, that interstellar visitors may be far more common than we ever imagined. And as our instruments become sharper and our eyes more patient, we will continue to catch glimpses of these silent messengers, drifting between the stars, passing through our system without warning, leaving behind only questions and wonder. In early October of this year, from October 1st to October 7th, the ExoMars and Mars Express orbiters witnessed a rare event, the passage of the interstellar comet 3I Atlas. This is, incidentally, the first interstellar object ever observed so close to Mars. The closest distance between the comet and the orbiters was about 30 million kilometers, enormous by ordinary standards. but in the context of interstellar travel, practically a brush with cosmic traffic. And in this episode, we'll explore what other Martian spacecraft managed to capture. All right, no long preface. Let's get straight to the point. The ExoMars spacecraft, orbiting Mars since 2016, carries a high-resolution camera primarily designed to study surface features and atmospheric phenomena. But 3I Atlas turned out to be an unbelievably faint target. Tens of thousands of times dimmer than the objects the camera is normally tasked with imaging. To capture it, mission operators had to push the camera to its limits, extending the exposure time to 5 seconds, taking dozens of frames, then processing and stacking them. The final result was a barely visible, pale white dot against the blackness of space. And yet hidden within that dot was something more. A faint halo of light surrounded the object. A coma, a thin gas, dust envelope formed as volatile materials evaporate under solar heating. The coma, stretching thousands of kilometers, confirmed that the object was indeed active. But the edges of the halo were lost in image noise, and no tail had yet formed. This is likely because, at the time of observation, 3I Atlas was still far from the sun, and the lighting was extremely weak. However, some scientists have pointed out that the absence of a distinct tail, even with early activity signs, could indicate unusual physical properties. One hypothesis suggests the object may be extremely dense and poor in volatiles, which would prevent the formation of a complete tail even when heated. Other researchers, the more skeptical and cautious kind, have noticed two curious features: the comet's exceptionally stable brightness and its unusually uniform reflectivity. Together, these traits hint at the possibility of metallic or composite surfaces. And those observations have fueled one of the most provocative ideas circulating online. What if 3I Atlas is not a natural comet at all, but an artificial interstellar object? It's a captivating notion. The arguments from proponents of the artificial origin hypothesis usually boil down to 3 points. Minimal deflection by the solar wind, as if the object possesses some form of active stabilization. Unusually smooth, uniform reflection, not at all like the irregular scattering from dusty or icy aggregates. A visible spectrum that, in some early observations, appears to lack the classic signatures of water vapor and carbon dioxide. However, most planetary scientists and experts in small body dynamics emphasize that these observations can still be explained by natural processes. The comet may have lost the bulk of its volatile materials long before entering our solar system. Its remaining surface could have become coated with dust, regolith, and micrometeorite-formed glass, creating a hardened crust resistant to further evaporation. The minimal influence of solar radiation pressure on its trajectory can be explained by its large mass and low surface-to-mass ratio. In other words, it has very little windage. Thus, despite 3I Atlas's unusual characteristics, its behavior remains within the expected bounds for a natural interstellar comet. But the story doesn't end here. Compared with ExoMars, the second Mars orbiter Mars Express also attempted to detect a visitor during this period. Its onboard camera, however, uses a much shorter exposure time, just half a second, and the resulting frames have not yet revealed a confident detection. Researchers plan to combine dozens of images in hopes of isolating the faint glow and confirming the comet's presence. Meanwhile, parallel observations were carried out using the Omega, Spicum, and Nomad spectrometers, which typically analyze the composition of the Martian atmosphere. With a bit of luck, they might capture reflected light from 3I Atlas and extract its spectral lines. It's unclear whether the comet is bright enough to leave a detectable signature, but the attempt itself demonstrates how flexible these instruments can be when pressed into unexpected service. One of the most intriguing twists in this story, as you know, came from a short series of images taken from the surface of Mars by the Perseverance rover. In one raw photo, the comet appeared as an elongated streak of light, almost cylindrical, igniting a wave of debate across scientific and media circles. But later analysis showed that this cylinder was nothing more than an optical artifact, a combination of long exposure, relative motion, and the rover's imaging geometry. A disappointment, perhaps, but also an important reminder of how challenging interpretation can be, even with modern technology, and just how crucial it is to consider environmental conditions. Meanwhile, the Curiosity rover was unable to capture 3I Atlas at all due to the comet's extreme faintness, its unfavorable viewing angle, and Curiosity's own hardware, which was never designed for deep sky observations. But we won't hold that against it. Its job is hard enough already. Other Mars missions also attempted to contribute. The Chinese orbiter and rover Zhurong, despite lacking dedicated astronomical instruments, transmitted telemetry about sky brightness and atmospheric conditions during the comet's passage data that may help refine orbital imaging parameters. India's Mangalyaan 2 mission, still in preparation, did not observe the comet directly. However, Indian astronomers coordinated ground-based telescope sessions with NASA's orbital measurements, adding valuable points to improve the trajectory model of 3I Atlas. In South Africa, observatories including the Meerkat radio telescope searched for possible radio emissions, but the comet proved far too faint and far too fast to produce a detectable signal. Nevertheless, the collaboration between so many nations revealed a striking truth. The study of interstellar objects is becoming an increasingly international endeavor. As specialists at the European Space Agency noted, the observation of 3I Atlas acted as a stress test for our current spacecraft and instruments. Trying to detect such a faint object from orbit around another planet pushes the limits of modern technology. And yet, the data collected by these probes has already provided valuable experience for future missions. One practical conclusion was especially important. The imaging modes originally designed for studying the Martian atmosphere can be repurposed to observe objects far beyond Mars's orbit. This means spacecraft can remain scientifically useful far longer than originally planned, extending mission lifetimes and dramatically improving the return on investment for every probe we launch. Meanwhile, researchers are now looking ahead. Additional observations of 3I Atlas are planned for November, using ESA's Jupiter-bound JUICE spacecraft. By then, the comet will be closer to the Sun and significantly more active. Evaporation should intensify, and a well-defined tail is expected to form, offering a clearer, more detailed look at the comet's composition. The JUICE data, expected in February 2026, will become a crucial complement to the Martian observations, giving scientists the ability to trace how the object evolves as it approaches and recedes from the Sun. And who knows, perhaps JUICE will detect something completely unexpected. A strange glow, perfect geometry, or behavior that seems to defy physics. Or perhaps it will detect nothing at all, should 3I Atlas decide to slip quietly out of the solar system, having completed its mission of observing humanity. Finally, the ongoing observation campaign ties directly into preparations for the European Comet Interceptor mission, scheduled for launch in 2029. This spacecraft will be positioned in a stable orbit around the L2 Lagrange point, patiently waiting for a suitable target, potentially even an interstellar comet. Unlike Mars orbiters, the Comet Interceptor will be able to rapidly change trajectory and perform a high-speed flyby of any incoming visitor. Now, that is impressive. The insights gained from studying 3I Atlas now, its faintness, its geometry, its unpredictable motion will help define the optimal observation parameters, camera sensitivities, and navigation strategies needed for such encounters. From a scientific standpoint, the significance of this work extends far beyond one solitary object. Every interstellar visitor carries clues about the physical and chemical processes unfolding in other planetary systems. By studying them, scientists can compare the building blocks of our solar system with those of distant stellar neighborhoods. Even fragmentary data, a few spectral lines of reflected light, or the chemical signature of a thin gas dust coma helps refine our models of stellar drift, planetary formation, and the violent processes that eject bodies from protoplanetary disks. In this sense, Comet 3I Atlas is an ambassador from another world, bringing whispers of ancient dust from interstellar epochs, or perhaps playing the role of a cosmic invader, depending on how dramatic you prefer the story to be. If you enjoyed the video and want to see more, please support the channel. It truly helps. Leave a like, subscribe, and drop a comment. Every action boosts the channel and helps new videos come out. Thank you for your support.